Now, the standard reduction potentials chart has many, many, many elements on it, but I'd like just to write a couple of them here. We've got silver and we've got iron, iodine, aluminum. And we can use this to solve some problems. For example, our first question is, predict whether iron 3 can oxidize iron iodide to iodine under standard conditions. Okay, so can iron react with iodide and oxidize it to form then, let's see, if iron is going to be oxidizing iodide, it must be reduced if it's an oxidizing agent. And so it's going to be reduced from iron 3 to iron 2, and iodide being oxidized is going to lose electrons and become a little bit more positively charged, go from I- to I2. So can this reaction occur spontaneously? Consider that one way to know whether a reaction is spontaneous is to say whether its E cell is positive or not. And so you can calculate the E cell for this reaction. You could say that, let's see, iron is being reduced, so it must be at the cathode, both consonants, and iodide is being oxidized, so it must be at the anode, both vowels. And so plug in for E cathode the standard reduction potential of iron 3, and plug in for E anode the standard reduction potential of iodide. And so you can get these values from up top. So let's see, iron 3 has a standard reduction potential of 0.77 volts, and iodine has a standard reduction potential of 0.53, but you are actually going to be using this exact value in your calculation. Really here, it's not the standard reduction potential of iodide we're using, but of the iodine, of iodine, the thing that is reduced. So plug in that exact number, and so you get 0.77 volts minus 0.53 volts, and that's 0.24 volts. That's a positive E cell, so having a positive value, we can say that that reaction is spontaneous, and so that iron 3 can oxidize iodide. But yet I think an easier way to solve this problem is just to use the diagonal rule. The question is, can iron 3 oxidize iodide? Can iron 3 react with I-? So, can iron 3 react with I-? Well, yes, it can. Recall that top left things can react with bottom right things. So, that reaction can occur. That's much quicker, isn't it? All right, so another question we have is, so please be sure that you can use the diagonal rule. That saves a lot of time. All right, so go ahead and calculate the standard EMF of a cell that uses silver and aluminum half reactions at 25 degrees Celsius, and then write the net ionic equation for the reaction that occurs. Okay, so we need to calculate the standard EMF. Let's see, so one way that we could do this is getting E cell is equal to E cathode minus E anode, but we don't yet know what is going to be at the cathode and what is going to be at the anode. I guess one way to consider that is to consider what is the reaction that will be occurring. And so we can decide what reaction is occurring by using the diagonal rule. So go up top, and we've got a system filled with silver and aluminum. What will be the spontaneous reaction that's occurring? Silver ion will react with aluminum. Diagonal rule says those will react together. And so that allows us to predict what will happen. Let's see. We know aluminum is going to react with silver ion and give these things. We can now know what is going to be oxidized. Aluminum is reacting, and it turns into aluminum 3. It's oxidized. Aluminum will be at the anode, and silver 1 turns into silver, into silver 0, so it is reduced at the cathode. And so we could use these values But before we do that, I'd like for us to go ahead and write that net ionic equation for what's actually going to be occurring. This what we've written right here is not actually the net ionic equation. It is not yet balanced for charge or the number of electrons. And so what we need is to balance for charge and electrons by writing the half-cell reactions separately. So aluminum turns into aluminum 3, and silver 1 turns into silver. But you'll see that aluminum, when it's oxidized, it releases 3 electrons, yet when silver is reduced, it only absorbs 1 electron. And so to balance these two half reactions to give our overall net ionic equation, we need to multiply this bottom equation by 3 so that then there will be 3 electrons absorbed when 3 electrons are released. And so there's going to be 3 silvers and 3 silver 1s and 3 silver solids. And this is actually going to be our net ionic equation. That is the final net ionic equation. And so now we can plug in for our E cell. We'll plug in for E at the cathode, and recall that at the cathode what is being reduced is silver. So we'll plug in for the standard reduction potential of silver 1. And then we'll subtract E standard at the anode, which was the standard reduction potential of aluminum ion. And so we'll plug in from the table up there, and we'll get 0.80 minus negative 1.66 volts. It gives us 2.46 volts. So this is the voltage of the cell that we should expect. But wait, shouldn't we have multiplied the standard reduction potential of silver by 3 times, being that 3 of them are reacting and 3 are being formed? Actually, no. Recall that standard reduction potentials are not affected by the coefficients in front. And so the standard reduction potential of 1 silver reacting into 1 silver solid is the same as 3 silver ions reacting into 3 silver solids. And so do not account for coefficients in these reactions, and do not flip around the signs of things either. Plug in the exact values that are provided in the table. Thank you for watching, guys.